Oh, chemistry. Chemistry's cool. I liked chem when I took it. It's not that terrible. So we're going to be talking about projections. So projections, mathematically, projection is formed by dropping a perpendicular from each of the points of an object onto a line or a plane. So suppose we have vector u and vector v, where vector v cannot equal 0, are two vectors with a common initial point, with theta, the angle between them, being between 0 and 180. The vector we obtained by projecting u perpendicularly onto the line through v is called my vector projection of u onto v, and is denoted as projection of vector u onto v, or projection subscript u times vector u, and this is considered a vector quantity. So this is my vector u, which is going this way. This is my vector v. So if I draw a perpendicular line from the end of the points onto the object or plane, this red line right here is going to be our projection of v onto u. Okay? Now the next one, we have our vector u. This is our vector v. So remember, in order to get our projection, we drop a perpendicular line from each of the points of the object onto the line or plane. So because u's head is at the top, I can therefore drop this perpendicular line right here. And from the tail of u and v, I can therefore draw my projection of v onto u, which is this green line right here. So in the first case, my theta is contained within u and the projection of v onto u. Well, it all depends on where vector u is, right? So if vector u is going upwards, then I can have my projection coming down. But if vector u is going to be is 0, vector v cannot be 0. So vector v can be the other vector going up instead of vector u. So when we do this, we have the projection of our v in terms of, let's look at our theta. So this is our theta value. This is our projection of v onto u, and this is our u. What trig ratio do you think we're going to be associating the projection with in order to find theta? What trig ratio? Let's see, what trig ratio in SOHCAHTOA has adjacent and hypotenuse? Cos. We're going to be associating this with cosine. So the projection of u onto v is defined by the projection of v onto u, is equal to the magnitude of u times cos of theta times the unit vector v. Okay? And my unit vector, we can always assume, is going to be a magnitude of 1. So by SOHCAHTOA, and its magnitude is the magnitude of the projection of u onto v is equal to is equal to the magnitude of u times cos theta times v. So the composition of u onto v is equal to the magnitude of u times the times cosine theta. So comp means component, my apologies. So the component of u onto v is equal to the magnitude of u times cosine of theta. So by using the dot product, we can also define the projection of u onto v by doing the following. So we know that u dot product v from, I think, 2 lessons ago is the magnitude of u times the magnitude of v times the cos of theta. Now, we can rewrite that. So we can also rewrite it as the dot product is equal to the magnitude of u times cos theta times the magnitude of v. Because of the commutative property, we can, when multiplying numbers or any terms, we can decide to switch the order and it will still give me the same thing. So now, if you want to solve for u, for the magnitude of u times cos theta, this gives us u dot product v divided by the magnitude of v. So because we already know the magnitude of u times cos theta is the same thing as in the projection of u onto v, we can say that the projection of u onto v is equal to the dot product of u dot product v divided by the magnitude of v times the unit vector v. Now, if we substitute our unit vector theory or concept from, I think, the second lesson, we know that the unit vector is just 1 over the magnitude of that vector times the vector itself. So the projection of u onto v is equal to u dot product v times vector v over the magnitude of v squared. And this is a vector quantity. So this is ultimately what we get to figure out the projection of u onto v. So now let's continue and let's see if we can do some examples together. However, we also have something called the scalar projection of u onto v. This is a scalar quantity and it is the scalar quotient of the projection vector. So hence, this is our vector, our calculating scalar projections. So we have the scalar projection of u on v is u dot product v over the magnitude of v, or the magnitude of u times cos theta, where theta is the angle between u and v. So the scalar projection of v onto u is exactly the same thing, except my denominator is the magnitude of u, or the magnitude of v times cos theta, where theta is the angle between u and v. So in general, u dot product v over the magnitude of v cannot equal u dot product v over the magnitude of u, and we will denote the scalar projection of u on v as the scalar projection of subscript v and u. Okay. So now let's all put this together and figure out how to use each and every one of these. So we have vectors a and b. We have vector a, which is -3, 4, and 6. We have vector b, which is -2, 2, and -1. So we want to figure out the projection of a onto b. We want to figure out the component of a onto b. And we want to figure out the scalar projection of a on b as well. So for A, we already know what my projection formula is. So I know my projection of A onto B is going to be A dot product B over the magnitude of B squared multiplied by my vector B. So can someone tell me what A dot product B divided by the magnitude of B squared gives me? Let's see if you guys can figure this one out. So you're just doing A dot product B divided by the magnitude of B squared. That's all you're doing. Don't worry about multiplying it onto vector B yet. So who can tell me what the value of my brackets gives me? Okay, so Priyanshu got 8 over 9. Did anyone else get 8 over 9? Did anybody else get 8 over 9? Okay, Ricardo got 8 over 9 as well. Perfect. So my bracket, I get 8 over 9. So this equals to 8 over 9, multiplied by my vector B, which is negative 2, 2, and negative 1. So now when I multiply my scalar into it, or my 8 over 9, I get the vector negative 16 over 9, 16 over 9, and negative 8 over 9. So that is my projection of A onto B. That is the vector that I get. So now for B, I want to get my component of A onto B. So I know that the component of A on B is the same thing as saying my projection, the magnitude of my projection of B on A. And that was based from the previous page. So my component of B onto A is going to be the magnitude of A dot product B divided by the magnitude of B. Can someone tell me what my component is going to be? 8 over 3. And this is going to give me 8 over 3. Perfect. And now I need to figure out my scalar projection of A onto B. So from the previous note, so my scalar projection of A onto B is just going to be the same thing as saying A dot product B over the magnitude of B. And we already got this answer, which is going to be 8 over. So the component gives you the magnitude, okay? So it just gives you the magnitude of that vector. However, the scalar, you don't need to take the magnitude of it. So if the scalar was a negative number, it would be a negative, right? However, with the component being the magnitude of that whole thing, if there was anything negative in that on the inside, we would have to take its true value, which is going to be, say, if it's negative 8 over 3, we would have to take the true value of 8 over 3. However, for the scalar projection, if, say, the numerator was a negative number, because I'm not taking the magnitude of it, I would just leave it as a negative. I think we have a couple more examples, and then that's probably it for today. So a box with a weight of 12 newtons rests on a frictionless ramp inclined at 25 degrees to the level ground. We want to find the magnitude of the force directed up the ramp that must be applied to keep the box at rest. So let's label this guy over here, vector R. So the weight of my box, so vector F at G, is going to get me 12 newtons, okay? And based off of what we know so far, this guy over here is going to be my projection of F on R. So I know this guy over here is 25 degrees. Now I need to figure out what angle I need to use to help me figure out how to solve this question. Remember, when we're talking about the projection of something, so from the first page, we know the projection of A onto B is the same thing as saying the magnitude of A times cos theta. So in order for me to figure this out, I need to use this projection over here, which means I need to use this angle right over here. So who can tell me how we can figure out what that green angle is going to give me? $65. So one way to visualize it is you can draw this parallelogram over here. So Priyanshu, what did you do to figure out how to get 65? If you don't mind explaining how you got 65 degrees. Yep, the red vector makes a right angle triangle with the floor. So we have this triangle right here. So all I can do is take 180 minus 25, or 90, 180 minus 90 minus 25, and this gives me 65 degrees as well. So now to find the projection, I can take the magnitude of A, or f of g in this case, so magnitude of fg times cos theta, which gives me the magnitude of 12 times cos of 65, which gives me approximately 5.07 newtons. Therefore, the force directed up the ramp needed to keep the box at rest is approximately 5.07 newtons. So now we may be asked to find the area of a parallelogram using the cross product, which means that our vertices might be in terms of a vector. So the area of a parallelogram is the product of its base and its height. The base of the parallelogram in the diagram is vector v, and its height is equal to u, vector u, times sine v. So if we're referring from this angle over here and we want to find h, we know h is the opposite side and u is the hypotenuse side. So if you do SOHCAHTOA, you know sine theta is equal to h over the magnitude of u, which means h is equal to the magnitude of u times sine theta. That is how we would find my height, which means that the area of the parallelogram having u and v, as its sides is the area is equal to the magnitude of u times the magnitude of v times sine theta, and which means that the area is equal to u cross product v. So we can also find the area of the parallelogram using the components of the two vectors by finding their cross product and then the magnitude of the cross product. So our next example is going to be finding the area of a parallelogram. So a parallelogram has vertices A, which is 4, 2, 1, B, which is negative 1, 1, and negative 3, C, negative 5, negative 2, negative 5, and D, 0, negative 1, negative 1. Let's name this A, B, C, D. So let's find the area of the parallelogram. So the area of the parallelogram is going to be my height, vector AB, cross product, vector AD. Based off the definition we got from the previous page. So this is equal to the magnitude of AB, cross product AD, vector AD. So now we're taking the magnitude of negative 5, negative 1, and negative 4. Cross product, negative 4, negative 3, and negative 2. Remember, to get AB, it's a head minus the tail. So negative 1 minus 4, 1 minus 2, and negative 3 minus 1. And AD would be 0 minus 4, negative 1 minus 2, negative 1 minus 1, which is from what we got before. So now we're going to put this in order. So we got negative 5, negative 1, negative 4, negative 5, negative 1, negative 4. And we have our next vector, which is negative 4, negative 3, negative 2, negative 4, negative 3, negative 2. Again, we disregard the first and the last. So what we're going to get is 2 minus 12, 16 minus 10, and 15 minus 4. So our vector becomes negative 10, 6, and 11. And because we want to find the area, which is the magnitude, I need to take the magnitude of negative 10, 6, and 11. And what we learned from this unit is we take it by squaring all of my components in the vector and taking the square root of it as well. So I get 100 plus 36 plus 121, and that gives me the square root of 257 units squared. Can we simplify this radical even more? Is this the most simplified it can get? This is the most simplified it can get. So this would be my final answer. Now for B, I want to find the area of triangle ABC. All right. Area of triangle A, B, and C. Now from regular geometry, I would know that the area of triangle ABC is just half the area of the parallelogram. So the area of my triangle is going to equal 1/2 of my cross product or magnitude of AB cross product AD. And we know that gives us half of root 257, which gives me an answer of root 257 over 2 units squared. And now for our last part of this lesson, we're going to get into some physics. So work, a dot product application. So work is done whenever a force acting on an object causes displacement of the object from one position to another. So the key ingredients to work is force, displacement, and cause. So in order for a force to qualify as having done work on an object, there must be a displacement, and the force must cause the displacement. So if you've taken physics, you probably have seen this 5,000 times. While it may not seem like hard work to hold on to a heavy object, if you do not move, you are doing no work. Force of gravity does not do work since it's a vertical force, cannot cause a horizontal displacement. Forces do work when there is some component of the force in the same or opposite direction of the displacement. So the work done by a force is defined as a dot product. So work is equal to the vector of the force, dot product, vector d. So which means I take the magnitude of the force times the displacement, the magnitude of the displacement times my angle and multiplying it by cosine. Where F is the force acting on an object, which is in newtons. D is the displacement caused by the force, usually in meters. And theta is the angle between the force and displacement vectors. Work is a scalar quantity. The unit of work is a joule. So example 4. A box is dragged 16 meters across the floor by a 75 Newton force at an angle of 35 degrees to the floor. It is then dragged a horizontal distance of 8 meters by the same force up the ramp inclined at an angle of 20 degrees to the floor. I want to determine the total work done by the force. So I'm dragging it across 16 meters, and this force makes an angle of 35 degrees. And it's being pushed, or it's being dragged across a level floor by a 75 Newton force. So this is going to be my force vector over here. And same thing over here. So it is then dragged at a horizontal distance of 8 meters by the same force up a ramp inclined at an angle of 20 degrees to the floor. So this guy over here is going to be 8 meters. I want to determine the total work that is being done by the force. So my first work, I need to determine two types of work. So the total work is from the first 60 meters and then from the 8 meters that was done after. So my first work force is going to be the magnitude of F, dot product, the magnitude of distance number 1, which is right here, which is 16. So 16 is distance 1. So I know my force is 75 newtons. I'm going to multiply that by my distance, which is 16, multiplied by my angle, which is cos 35. So I get 75 times 16 times cos 35, and this gives me approximately 982.98 joules. So this is the amount of work done in the first 16 meters. Now I have to figure out how much work was done in the last 8 meters. So my second work is actually up a ramp right here. So I know my horizontal distance is 8 meters, but I need to figure out how much I went up that ramp. What was the distance I traveled going up that ramp? And the ramp was inclined at an angle to the 4 of 20 degrees. So this guy over here, I know I drew a bit exaggeratedly right here. Let me just fix this. This angle right here is going to be 20 degrees. This is my horizontal distance to the floor, which means that I need to figure out the distance I traveled on the second step. So I need to figure out what my distance was. So I'm going to use simple SOHCAHTOA. So I'm going to use cos 20 is equal to 8 divided by the magnitude of my second distance up the ramp, which means that my distance 2, my vector of distance 2 is going to be 8 divided by cos of 20, which gives me approximately 8.51 meters. Which means that the second distance, I had to drag up 8.51 meters. Okay, so this is 20 degrees, which means this guy right here is going to be 15, which is the angle I need to use to determine my work in the second equation. So I need to figure out how much work I do in the second stage of this activity. So I take F dot product D2, which gives me the magnitude of F times the magnitude of the second distance times my cos of theta. So I know F is 75 newtons still. I know my second distance is about 8.51 meters. And my cos theta, the angle is going to be 15 because I'm dragging it 15 degrees upwards. So when I do all of this calculation, I get approximately 616.75 joules. So in order to figure out my total work, I need to add my work from the first part of this activity and my work from the second part of this activity as well, which means I get 982.98 plus 616.75 is equal to 1,599.73 joules of total work. And the reason why I'm doing the cos of 15 is because I'm walking up this ramp right here, and my vector force is already up here. So it's acting on the angle of 15 degrees, which is why I use cos 15 and not cos of 20.